Welcome to NoFace TechTalk, the voice behind the code. Deliberately anonymous, focusing attention on the human or conceptual forces behind the tech, the voice behind the code.
Today, we're diving into a really fascinating exploration of artificial intelligence, looking at where it's been, what it can actually do right now, and, well, where it might be headed.
Yeah, it's a big topic.
It really is. Our mission for this deep dive, to try and cut through, the mountains of hype and maybe fear
There's
sometimes.
definitely a lot of that around.
Yeah, and get a clearer picture of what these AI systems are and maybe aren't capable of, understand their real limitations, and think about the questions these technologies raise as, well, as they become more and more part of our lives. Think of it as maybe a shortcut to being better informed in this landscape that's changing so fast.
Exactly. And what we're exploring here offers a really nuanced view. It highlights both the remarkable successes, the things AI has achieved in recent years, but also the fundamental challenges that are still very much unsolved.
Right.
It shows just how complex and, yeah, sometimes contradictory the whole field is today.
It sounds like quite a journey through the topic. I mean, there's even this slightly ironic story of getting hilariously lost inside the Google Maps building on the way to an AI meeting.
Huh. Yeah, the irony is pretty thick there.
Right. And then grappling with these really profound questions about what it would actually take for machines to have something like consciousness or just basic common sense.
Mm-hmm. Big questions.
Okay, let's unpack this then. Maybe we can start by setting the scene at Google. They're a company that's gone, all in on AI.
Oh, absolutely. Larry Page and Sergey Brin, the founders, they've been driven by big ideas in AI for a long time.
And they brought in people like Ray Kurzweil, right? He's famous for pushing this idea of an AI singularity at that point where computers actually surpass human intelligence.
That's right. Google hired him specifically to help, well, make that vision happen. They created Google Brain. They acquired startups like DeepMind.
DeepMind, yeah. Their original mission statement was incredibly ambitious, wasn't it? Something like it.
Solve intelligence and use it to solve everything else.
Yeah.
Pretty grand.
Wow. And what's fascinating is the contrast, like you said, with the early days, back in the 70s.
Oh, completely different vibe. Achieving human-like intelligence felt, well, incredibly distant. Someone described it as 100 Nobel Prizes away.
100 Nobel Prizes.
Yeah, and you had skeptics like John Searle and Hubert Dreyfus who basically argued it was fundamentally impossible.
So it was more like this deep intellectual adventure back then, wrestling with big ideas, but no sense of immediate danger.
Pretty much. Though you did have people like Douglas Hofstadter who believed, in principle, it could be done. Arguing that a brain follows physical laws and a computer can simulate anything, theoretically.
But now, fast forward a few decades, and it feels like, well, depending on who you ask, we're either making huge progress or maybe still barely scratching the surface of those huge goals.
Exactly. And this exploration really highlights that turmoil, these conflicting views on whether true AI is like right around the corner or maybe centuries away.
Or if it's going to solve everything or, cause huge problems.
Right. Which really brings us to the core question driving this whole thing. How far has artificial intelligence really come? It tries to get a real handle on the state of affairs by looking closely at where AI clearly shines today. Things like playing complex games, translation,
Okay.
and then contrasting that with areas where it really, really struggles. Tasks that we humans just take completely for granted, like recognizing objects using common sense or understanding the subtle bits of language.
Okay, so before we dive deeper, maybe let's get some terms straight, because the way AI gets talked about in the media, it can be super confusing.
Oh, definitely. Good idea.
So artificial intelligence, that's the big umbrella, the whole field.
Right. The broad concept.
Then machine learning is a part of AI, a subfield.
Correct. An approach within AI.
And deep learning is just one specific technique within machine learning. But often in the news, when they say AI, they really just mean deep learning.
Exactly. That's a really common inaccuracy.
Yeah.
And it's important to be clear about it.
And that distinction, it actually goes back to an early split in how researchers thought about AI.
Yeah, a kind of philosophical split.
Yeah.
For the first maybe 3 decades, the main approach was what's called symbolic AI.
Symbolic AI. Okay.
This treated intelligence as basically processing symbols based on rules that were programmed in explicitly.
Yeah.
Think about puzzles like the missionaries and cannibals problem.
Right. I remember that one.
The symbols, like missionaries, they only have meaning based on how the program is told to manipulate them, according to the rules. There's no actual human understanding of what a missionary is.
Got it. So it's all about the programmed logic.
Precisely. And expert systems, like one called MyCIN, used in medicine back in the day, were built like this, trying to basically download human experts' knowledge into a set of if-then rules.
And the other side of that split?
That was subsymbolic AI, often called connectionism. This took more inspiration from the brain's structure.
Ah, the brain-inspired approach.
Yeah. It focused more on the computational architecture itself and on learning directly from data rather than pre-programmed rules.
Hmm.
The perceptron, invented way back in the late 1950s by Frank Rosenblatt. That's a key early example.
The perceptron. Right, that was modeled kind of like a neuron, wasn't it? Summing up inputs and then firing if it hit a certain threshold.
Exactly. And the core idea was that the knowledge wasn't in those explicit rules anymore. Instead, it was encoded in the numerical weights, the strengths of the connections between these artificial neurons.
And those weights were learned.
Right, learned through processes like conditioning or supervised learning. You'd show the system examples, it produces an output, and then you give it feedback, a supervision signal, to adjust its weights. A bit like, training a dog with treats.
Okay, I see. But didn't AI go through some rough patches, these AI winters?
Oh yes, this exploration definitely points that out. Periods where there were these big, maybe overblown promises led to AI winters, when funding just dried up. Especially for symbolic AI, actually, after some critical reports came out in the mid-70s.
But the neural network idea, it came back.
It did. Neural networks saw a resurgence, particularly connectionism, in the late 1980s when funding picked up again. And then really since the 2010s, deep learning, which is basically neural networks with more than one of those hidden processing layers, has become the dominant approach, the leading paradigm.
Okay, so that brings us to the modern era. And this is where things get really interesting, right? We've seen huge progress in areas like computer vision, object recognition.
Dramatic progress, yeah. Driven heavily by deep learning.
And the key technology there is convnets, convolutional neural networks.
That's right. Convnets are central to this success. Their structure is, it's somewhat inspired by the visual cortex in our brains. They have these layers of units, or neurons, that act as detectors for increasingly complex features. So early layers might detect simple things like edges or corners, and then later layers combine those to detect parts of objects and then whole objects, building up these hierarchical maps.
Fascinating. And what really enabled this breakthrough? Was it just the networks?
Well, the networks were key, but so was data. A huge breakthrough was ImageNet.
Ah, ImageNet, that huge database of images.
Exactly. Millions of images, each one linked to a noun and structured using something called WordNet, which is like a big hierarchical dictionary of English words.
And how do they even label all those millions of images?
That's where platforms like Amazon's Mechanical Turk came in. This exploration playfully calls it artificial intelligence.
Huh, like the old chess machine hoax.
Exactly. They basically paid tens of thousands of humans, workers, small amounts to label all those images. Fei-Fei Li's team at Stanford spearheaded that massive effort, got it done in just a couple of years. It was huge.
Wow, okay. And then came the 2012 ImageNet competition. That was a big moment.
Yeah. A massive turning point. A convnet called AlexNet, developed by Alex Krasevsky and his colleagues under Jeffrey Hinton, just blew the competition away. It achieved this astonishing jump in accuracy compared to the older methods.
And that sparked a lot of excitement. Claims about reaching human levels.
Huge excitement, yeah. And by 2015, you had companies like Baidu and Microsoft claiming their systems were surpassing human-level performance on that specific ImageNet task.
But you're saying we need to be careful with those claims.
Absolutely. We should be really cautious. This exploration points out that the human-level comparison often comes from very narrow experiments. Like one researcher, Andrzej Karpathy, specifically trained himself just on that task and got about a 5% error rate.
Right, but that's not really the same as general human vision.
Not at all. Human vision is so much richer. It's about understanding complex relationships between objects, what actions are happening, the whole meaning of a scene. Current systems are still pretty far from that, even if they're good at labeling a single object.
Okay. Let's maybe switch gears a bit then. What about language, natural language processing?
Deep learning also had major successes there, actually around the same time, starting about 2012, particularly in speech recognition.
Speech recognition, right, like dictation software, smart assistants.
Yeah. There was talk of the biggest single improvement in 20 years. And accuracy now, in quiet conditions, can be really high, like 90–95%.
That's impressive. but not perfect.
Definitely not perfect. And you still get these kind of funny errors sometimes, right? Like moose being transcribed as moose or bareheaded coming out as bareheaded.
Right.
These little slips, they kind of reveal that there's still a fundamental lack of true understanding going on. It's matching patterns, very sophisticated patterns, but not really getting the meaning.
And other language tasks, things like translation or answering questions, are they harder?
Generally, yes, even harder. This exploration talks about ways to represent words using word vectors, like the word to-vec technique.
Word vectors, what are those?
They're basically mathematical representations of words, capturing relationships based on how words tend to appear near each other in massive amounts of text.
Okay.
And this allows for some cool things like analogies. The famous example is king minus man plus woman mathematically results in a vector very close to queen.
Wow, that's clever.
It is clever, but it also surfaces biases that are just sitting there in the training data. So you get things like man is to woman as computer programmer is to homemaker.
Ooh, yeah, that's not good. Shows the bias in the data it learned from.
Exactly. And then for translation, neural machine translation systems, like the one Google Translate switched to in 2016, they use these big encoder-decoder networks.
How do they work?
They're trained on enormous data sets of parallel sentences, like millions of sentences already translated by humans. The encoder reads the input sentence and creates a sort of abstract representation, and the decoder turns that representation into the output sentence in the target language.
And they're pretty good now, right? Google Translate seems much better than it used to be.
Often, yes, very impressive. But the exploration also shows examples where translations can still be quite inaccurate, or they lose the subtlety of the original language, or sometimes they just become humorously nonsensical, like a story about a restaurant where someone getting bent out of shape is translated literally into French, which makes no sense.
Right, literal translation fails.
Yeah, and there was an issue with older versions of these networks where if the sentence got too long, they could sort of forget the beginning by the time they reached the end. Those specialized components like LSTMs helped with that memory problem.
Okay. And what about question answering? I remember IBM's Watson beating humans on Jeopardy years ago. Was that real understanding?
Well, that's debated. This exploration discusses whether Watson was truly answering questions in a human sense, or if it was more like incredibly clever high-speed pattern matching combined with instant access to just vast amounts of data.
Because Jeopardy.
Yeah.
Questions have certain patterns.
They often do follow predictable structures, yeah.
Right.
And Watson was trained on something like 100,000 previous Jeopardy clues. Plus, it didn't have to buzz in physically, which is a speed advantage.
I see. And what about things like the SQUAD dataset? That tests reading comprehension, doesn't it?
Sort of. SQUAD asks programs to find and extract the answer to a question from a given paragraph of text. The answer is guaranteed to be right there, verbatim in the text.
So it's more like answer extraction than actual reading comprehension.
Exactly. True reading comprehension requires you to understand implied meanings, synthesize information, use background knowledge, things these systems generally can't do.
Like understanding sarcasm or subtle context.
Precisely. Or just basic common sense about the world, like knowing that a Burt burger isn't actually just great, or those Winograd schema examples.
Remind me what those are.
They're pairs of sentences where changing just one word flips the meaning, specifically who a pronoun like they refers to. For example, the city councilman refused the demonstrators a permit because they feared violence versus because they advocated violence.
Ah, right. In the first one, they is the councilman. In the second, they is the demonstrators.
Exactly. And you know that instantly because of your common sense, your knowledge about social situations, permits, protests. Current NLP systems really struggle with that kind of inference. It shows how far they are from genuine human understanding.
So, okay, despite these amazing triumphs in vision and parts of language, there are still some really significant limitations.
Absolutely. Current AI, especially deep learning, has major limitations. One big one that comes up, particularly with self-driving cars, is the long tail problem.
Full long tail. What's that?
It refers to the enormous number of very rare but totally possible unexpected situations, edge cases, that an AI system might run into.
Things it hasn't seen much or maybe ever in its training data?
Exactly. Think about driving. Red lights, stop signs, those are super common. The AI sees millions of examples. But what about, say, a flooded road? Or a police officer manually directing traffic because the lights are out? Or construction workers using hand signals?
Right, those are much rarer.
Much rarer. Human drivers, we handle these using common sense, improvisation, understanding the context, Current AI systems, they struggle immensely because they just haven't been explicitly trained on enough of these rare edge cases from the long tail of possibilities.
And that leads right into this core issue you mentioned, the lack of common sense.
It really does. It's arguably the biggest barrier. Humans have this huge reservoir of intuitive knowledge. How the physical world works. Gravity, objects falling, liquids spilling. And how the social world works. Why people do things. Social conventions, like why there might be salt lines on the road in winter, or how to interpret body language at a broken traffic light.
Yeah, stuff we don't even think about. We just know.
Exactly. And the argument presented is that we can't, or maybe shouldn't, fully trust autonomous systems like self-driving cars until they have something similar. Something akin to this human-like common sense that lets us predict, adapt, and truly understand what's going on.
Okay, so lack of common sense is one big problem. What else?
Another major one is brittleness and vulnerability. The systems can be easily fooled.
How so? You mean like hacking?
Sort of, but sometimes it doesn't even require sophisticated hacking. This exploration describes adversarial examples. These are tiny changes made to inputs, images, sounds, text, often completely imperceptible to humans, that can cause the AI system to make completely wrong classifications.
Tiny changes, like what?
Like adding carefully crafted, almost invisible noise patterns to an image of a panda that makes the system classify it as a given with high confidence. Or putting specially patterned eyeglasses on someone that fools facial recognition systems.
Ooh.
Or even just putting small, inconspicuous stickers on a stop sign that makes a self-driving car's vision system misread it as, say, a speed limit sign.
That's genuinely alarming. Especially for things like self-driving cars or medical diagnosis AI.
It absolutely is. And it makes you wonder, doesn't it? What are these networks really learning if they can be tricked so easily by subtle, often irrelevant changes? Is it genuine concepts or just superficial statistical patterns?
Good question. Are people working on defenses?
Oh, yeah. Researchers like Ian Goodfeller, who discovered some of this, are working hard on defenses. But he's quoted saying something like, almost anything bad you can think of doing to a machine learning model can be done right now. And defending it is really, really hard. Feels a bit like a game of whack-a-mole right now. You fix one vulnerability, another pops up.
So brittleness, vulnerability, what else?
The black box problem is also a big one.
The black box, meaning we don't know how they work inside.
Pretty much.
Yeah.
The decisions made by these complex deep neural networks with millions or billions of parameters are often incredibly difficult, if not impossible, for humans to fully understand or interpret.
So when they make a mistake, we don't always know why.
Exactly. Which makes it really hard to predict when they might fail, or to diagnose the failure, or to reliably fix it. Their impressive abilities have to be balanced against the fact that they can and do fail unexpectedly in ways we can't easily explain.
Okay, so all of this, the long tail, lack of common sense, brittleness, the black box issue, it points towards what this exploration calls the great AI trade-off, right?
Yes, exactly. The great AI trade-off. It's this tension. How much should we go full steam ahead, embrace AI's powerful capabilities, which definitely have the potential to improve lives, maybe even save lives in areas like medicine?
It's unbelievable.
Versus how cautious should we be given these known problems, their errors, the potential for bias baked into them, their vulnerabilities, this lack of transparency?
It mentions Andrew Ng calling AI the new electricity.
Yeah, but the counterpoint made is that we actually understood electricity pretty well before we rolled it out everywhere. That's maybe not quite the case for many complex AI systems being deployed today.
Wow.
We don't fully understand their failure modes.
So the trade-off includes the question of how much humans need to stay in the loop supervising these systems.
Precisely. How much autonomy is safe to grant them? It's a really critical question.
And this also touches on ethical issues beyond just safety.
Oh, definitely. Big ethical issues. Concerns around face recognition technology, for example. The potential for misuse and surveillance or biased identification.
And some companies are actually pulling back on that.
Yeah, it mentions companies like Google and Microsoft taking steps to limit who can access their general face recognition services, specifically because they're worried about the potential for abuse and the need for regulation.
Which brings up regulation. Who should be deciding the rules?
Well, the argument made very strongly is that it shouldn't just be left to the AI researchers and the tech companies themselves.
Right, because it affects everyone.
Exactly.
Yeah.
The problems are fundamentally social and political, not purely technical. So you absolutely need diverse perspectives, ethicists, policymakers, social scientists, the public involved in shaping how this technology is developed and deployed.
And then there's the whole value alignment problem, making sure AI does what we actually want it to do, ethically.
Yeah, that's maybe one of the deepest challenges. How do you ensure an AI system's goals or values align with human values? Especially when, well, human values aren't exactly simple or universally agreed upon.
Like the trolley problem for self-driving cars.
That's the classic illustration, yeah. Should the car swerve to save 5 pedestrians but potentially harm its passenger? Or protect the passenger at all costs?
And surveys show people are conflicted.
Very conflicted. People might say, in theory, that the car should sacrifice the passenger for the greater good, but then ask if they'd buy a car programmed to do that. The answer is usually a hard no.
Yeah, I can see that. So programming morality is tricky.
Immensely tricky, maybe impossible in a way that satisfies everyone.
Okay, so if current approaches, especially deep learning, seem to be hitting this kind of barrier of meaning or common sense, are people looking at other ways to build intelligence?
Yes, definitely. This exploration mentions other approaches. For instance, attempts to directly build knowledge into systems, like the Psych project.
Psych? What's that?
It's a really long-term, large-scale effort using symbolic AI. It started way back in the 1980s, actually. The goal was, and still is, to manually encode millions of pieces of human common sense knowledge, facts, and rules about the world into a massive knowledge base.
Manually encoding common sense, that sounds like a huge task.
It is enormous. Psych has apparently amassed something like 15 million insertions, but its founder, Doug Lanatt, guessed they might only have about 5% of what's ultimately needed for true human-level common sense.
Wow, only 5% after decades.
Yeah, and a big challenge, similar to old expert systems, is capturing what's called tacit knowledge.
Tacit knowledge, the stuff we know but can't easily explain.
Exactly. Things we know intuitively, things we know how to do, but find it hard to articulate explicitly as rules or facts. And Psych relies on humans trying to translate their knowledge into formal logic, which is really hard for tacit stuff.
So is the argument that common sense can't just be captured by listing millions of facts?
That's a core argument presented here, yeah. That common sense and also things like abstraction and analogy making are just fundamental to how humans think in a way that goes beyond vast databases or simple logic.
Abstraction and analogy, like seeing similarities between different situations.
Exactly. It uses examples like visual Bongard problems, where you have to figure out the abstract rule that separates two groups of simple diagrams, or letter string analogies.
The letter string analogies, like the ABC at ABD example.
Yeah. If ABC changes to ABD, what should PPQRRs change to? Most humans intuitively say PPQR, not PPQRR.
Right, because you see the pattern is changing the last element of the sequence, and you implicitly group TPQRSS as elements.
Precisely. You perceive the subtlety of sameness and perform what Hofstadter calls conceptual slippage. You adapt the rule to the new context.
And AI struggles with that kind of flexible analogy.
Very much so. There were projects like Hofstadter's own copycat program that tried to build systems capable of this kind of analogy making using different ideas like active symbols. But they really only scratched the surface, couldn't handle more complex, open-ended problems.
And these systems also lacked something else, metacognition.
Right. Metacognition, the ability to think about your own thinking, to reflect on your thought processes, recognize when you're stuck or when an approach isn't working. Humans do this all the time. Current AI systems generally lack this kind of self-awareness or self-perception.
Which probably hinders their ability to learn and adapt effectively.
Seems likely, yes.
This exploration even touches on a really fundamental idea, embodiment, the need for a physical body.
Yeah, it brings up the argument, which was famously part of Mitchell Kapoor's long-running bet with Ray Kurzweil.
The bet about AI passing a Turing test by 2029.
That's the one. Kapoor's side of the argument, essentially, is that, true, human-level intelligence might actually require having a physical body and experiencing the world directly, interacting with it.
Why? To gain that tacit knowledge.
Exactly. The idea is that so much of our common sense, our intuitive understanding of physics, biology, social interaction, comes from the non-linguistic experience of being alive, having a body, moving through the world, manipulating objects. Things you can't just get from reading text or looking at pictures.
So intelligence isn't just about algorithms and data. It might need grounding in reality.
That's the argument.
Yeah.
And while it's still pretty speculative, it's an idea that seems to be gaining traction among some researchers today, even people like Andrej Karpathy. It suggests that maybe replicating intelligence requires a really fundamental shift in how we design AI-needing systems that learn through embodied experience like human infants do, developing intuitive physics and interaction skills.
Wow, okay. We have covered a lot in this deep dive. From those early, really ambitious dreams of AI
Yeah, the solve intelligence goals,
to the dramatic rise of duck learning, especially in vision and language.
the breakthroughs with ImageNet, translation, speech.
But then hitting these very real fundamental challenges that are still here. The brittleness, the shocking lack of common sense sometimes.
The adversarial examples, the long tail problem.
And ultimately, this profound mystery of what genuine understanding even is and whether machines can achieve it.
Yeah. And what we've explored really reminds us, I think, that despite AI getting incredibly good at certain narrow tasks,
Like playing Go or classifying images.
right? Despite that, general human intelligence, with its incredible robustness, its flexibility, its built-in common sense, its deep capacity for understanding context and meaning,
Yeah.
that's still largely elusive for machines.
And those predictions about when AI would finally reach human level, they keep getting pushed back.
Consistently miss the mark. All those predictions from decades past 10 years, 15 years, 25 years away haven't panned out. That long bet between Kurzweil and Kapoor about 2029. Well, the perspective presented here definitely leans towards Kapoor's view, that human intelligence is something amazing, subtle, still poorly understood, and probably not going to be duplicated wholesale anytime soon.
So the immediate worry maybe isn't some superintelligence taking over.
Probably not the immediate worry, no. The bigger concern in the short term seems to be our own human tendency to anthropomorphize these systems, to overestimate their understanding and give them too much trust.
Because they seem smart in some ways, we assume they're smart in all ways.
Exactly. And we forget how brittle and vulnerable they still are underneath. It's put it out quite starkly that the most worrisome aspect of AI systems in the short term is that we will give them too much autonomy without being fully aware of their limitations and vulnerabilities.
That great AI trade-off, again, balancing the progress and the real excitement with a necessary dose of caution.
Yeah. And deciding how much we as humans need to stay in the loop. That's a decision you, the listener, are probably already facing as these AI tools pop up everywhere at work, in your search engines, in your apps.
And it leaves us with this really powerful closing thought, doesn't it? Echoed throughout this whole exploration. Can machines truly understand human language or the incredibly complex world around them until they possess something genuinely akin to human common sense? That ability for abstraction, analogy, that grounding that comes from real-world experience.
And if the answer is no, or at least not, does that fundamental lack of deeper understanding inevitably make them fragile, unreliable, no matter how sophisticated or capable they might seem just on the surface?
It's certainly something worth thinking about long after this conversation ends. This deep dive has really just scratched the surface of these huge, fascinating questions. Thank you for joining us. If you enjoyed this episode, like, share, and drop a comment below. Don't forget to subscribe for more faceless tech deep dives. Until next time, stay curious.